Okay, welcome back to our seminar, Toronto Air Seminar, and today's talk will be given by Matthew on the convex relaxation for geometric problems in robotics. Matthew is a PhD student in the Space and Terrestrial Autonomous Robotics System Laboratory at the University of Toronto Institute for Aerospace Studies. His research applies the theory of convex optimization to estimation, learning, and planning tasks, which are crucial to safe and effective autonomous robotic system. Yeah, Matthew, take it away.
Thank you so much, Reinhard, and thanks again for the invitation to present today. So yeah, I'll be talking a bit about a few topics, all related to convex relaxations and all relevant to problems in robotics. Okay, so as a brief rundown, I'm going to give a little introduction of what my research is about and some basic background information. The first sort of problem we'll look at in detail is this idea of globally optimal sensor calibration. Then we're going to pivot a bit, but there'll be a link between the two topics to inverse kinematics. And finally, I'll discuss some ongoing work about deep representations of robot geometry, so how they can be used in representation learning and yeah, basically machine learning pipelines. Okay, so my research as a grad student has covered a variety of applications, including communication policies for collaborative SLAM, sensor calibration, and at this point, I realized that there was some links here that I was kind of often looking at problems involving convex optimization. So I got into some inverse kinematics work that looked at it through this lens as well, and then moved towards some representation learning that also used the theme of convex optimization. And finally, I'm currently collaborating with a colleague on some inertial parameter identification, and all of these applications did utilize the theory of convex optimization in some way. So today, I'll be focusing on these three applications. We'll go in a bit of detail in each of them. And more specifically, we're going to talk about convex relaxations for quadratic optimization problems or quadratic programs of this form. You've got a quadratic form as your cost function and some equality or inequality constraints here. And we're going to look at non-convex problems, but then we'll do convex relaxations of them. Okay, so typically an optimization problem's objective function can have local suboptimal minima like this. And a common strategy is to relax this cost function with a surrogate convex cost that is easier to optimize and ideally yields a similar optimal value. So similarly, a convex function like a two-dimensional quadratic surface here, when restricted to a non-convex domain like a circle, can lead to a non-convex optimization problem. And relaxing the domain to a larger convex superset, for example, the interior of the circle, can simplify an optimization problem and help in a lot of cases. So why is this useful? Convex optimization problems, which are defined as problems that have both a convex cost and a convex domain, are in general much easier to solve because every local minimum is a global minimum. So it's sort of like a bowl-shaped surface in higher dimensions, and they're much easier to solve. Okay. So why is this relevant to someone studying robotics? And we're going to see why this should matter. So the first one is that the idea of certifying the global minimum of an estimation or perception problem provides robots with an additional form of reflexivity, a way of monitoring themselves to decide when they need to get more data or conduct something differently. And it complements other notions of reflexivity like probabilistic uncertainty in an estimate or notions of observability of a certain problem. So we'll see it kind of fits in nicely and it provides this layer of reflexivity or reflexiveness. Also, in many problems, just choosing the best representation of a robot and its geometry and its environment's geometry leads to an efficient and elegant solution. So researchers have found that by applying convex relaxations to these quadratic optimization problems we're going to formulate, you get fast and efficient algorithms. So ultimately, what we want to do is prevent tragedies like Asimov's famous tumble down the stairs here by providing robots with certifiable perception and efficient motion planning and other control and other task-based goals in a way that's efficient and certifiable. Okay. So moving on now to this idea of globally optimal calibration. The term hand-eye calibration refers to determining the extrinsic transformation between a robotic hand and a camera or eye mounted on it. So this is a very common sensor configuration, and the solutions often assume the presence of a target like a checkerboard with known geometry. The formulation of hand-eye calibration we'll be talking about today is often called the AX equals XB problem, because this simple kinematic equality holds for the relative motions A and B of two reference frames related by an extrinsic calibration, an extrinsic transformation X. So in general, any sensor able to measure its own motion, often called ego motion, can be used in hand-eye calibration. And our solution isn't really just limited to an actual hand and an eye. Another point to bring up is that you can have a monocular camera that cannot resolve the scale of its motion. And that's an important detail here. So it can be not a stereo camera, but a monocular one that can't resolve the scale of its motion. And we're also not limited to actual hand-eye configurations. You can think of any sensor mounted on a platform as playing this role, and each sensor just needs to be able to measure its ego motion, so it can apply to aerial vehicles and ground vehicles that don't look like an actual hand and an eye. And it's a really important problem because you can't fuse information from multiple sensors unless you've figured out this transformation between them. So a very brief survey of recent hand-eye calibration work, recent being the last decade, because this is a very, very old field. So Heller and others provided a method that provides weak certification guarantees and some pretty good empirical performance, but it's a slow algorithm and doesn't handle the monocular case. Berkshire and Teller provided a principled maximum likelihood cost function, and they explore observability requirements for a unique solution to exist, but their algorithm doesn't provide any optimality guarantees. Furr and others produced a nice software package with robust and probabilistic cost formulations, but they didn't investigate the target-free or monocular cases. And somewhat similarly to my work, Wei and others tackled the monocular case using a convex relaxation-based approach, but they don't provide any guarantees on performance or certification capability. So contrastingly, my approach doesn't require a target. It can incorporate monocular camera, and it's guaranteed to produce a certifiably globally optimal solution when measurement noise is bounded, which we'll discuss in a little bit. I just want to reiterate that there's a ton of active work in this area. So this is just a representative slice to contrast with ours. So a bit more about the motivation for needing to actually certify a solution. Why is this important? So simply put, the world's complicated and safety is always critical. And in addition to probabilistic measures of uncertainty and classical definitions of robustness, an algorithm which can provide a certificate of actually having the global optimum to its formulation lends this complementary layer of safety to complex multi-sensor systems. So this has been applied to problems in SLAM, where you have efficient solvers that are able to certify the global optimality of solutions. And there's also been active work on robust point cloud estimation as well, point cloud alignment as well. And if autonomous mobile robots are to become productive presence in unstructured environments like roads, homes, construction sites, they have to incorporate precise and practical safety guarantees. So without accurate extrinsic sensor calibration, robots can't perform SLAM and other tasks involving multiple sensors. So it's sort of a very important early step in getting any robotic system with multiple sensors to work. Okay, so to get into some of the technical details, we've seen that this hand-eye calibration problem is all about determining the extrinsic transformation between a sensor coordinate frames A and B, and we'll denote this as theta for formulation here, or capital theta. So this transformation is represented by a member of the special Euclidean or SE3 matrix Lie group, which contains a member of the special orthogonal or rotation matrix group, SO3. And this can be defined by quadratic equality constraints here. So there's orthogonality of rows and columns, and then instead of the determinant being equal to 1 for a rotation matrix, you can do a quadratic cross-product based relationship here. So the absolute poses relative to some fixed world frame of the two sensors' coordinate frames are related by this extrinsic transformation. You can manipulate this relationship to get a relationship between the relative motion between the sensors at each time step, and then produce an error residual E that's linear in this extrinsic theta. So if you treat the sum of the squares of these error residuals as our cost function, subject to these quadratic SO3 constraints, we get a quadratically constrained quadratic program that we'll call our primal program, or P. So once again, note that the second sensor B has an inherent scale ambiguity, which we'll call alpha, because if it's a monocular camera, it won't be able to figure out the metric scale of its motion. So we've got a quadratic formulation, but you'll note that these quadratic equality constraints are in fact non-convex. So this is a difficult to solve problem formulation. There's tons of local minima. So what can we do with this formulation? So the approach we'll be using is to take what's called a semi-definite programming relaxation. So we've got our standard primal problem here in this form that we've seen. And you can rewrite this using the trace product and this Z matrix, which is kind of the outer product of the vector X. And this is an equivalent formulation. And then if you relax this requirement that Z's this rank 1 outer product, so if you remove the rank 1 requirement, which is a non-convex difficult constraint to enforce, and instead replace it with this semi-definite, positive semi-definiteness constraint, you've relaxed the problem to a simpler to solve and convex semi-definite program. You can also take another route to this by taking the Lagrangian dual of your original problem, and then once again taking the Lagrangian dual, and you'll see that there's a nice relationship between these problems, and there's a primal and dual pair of convex semi-definite relaxations. So when you take this relaxation, there's this notion of the duality gap. So in many cases, this can be tight, which means that you can solve the simpler convex problems to get a solution to your original primal problem. And as we mentioned earlier, it's much easier to solve globally these convex optimization problems. So this is a desirable property. And the question we want to ask is, for our problem, when is this the case? When is it in fact a zero duality gap such that we can just solve this relaxed problem and extract our original solution? So in pursuit of that, we use this recent notion from Cifuentes and others of the stability of a semi-definite programming relaxation. And the notion that we'll apply here is we'll take all the measurements that our sensors get, so the rotations, translations, and scaled translations, we'll put them all in a vector over all time steps and call it lowercase theta. And we'll treat that as a parameter of the cost function of our QCQP formulation here. And then you can easily show that when there's no noise in your sensor measurements, you have this theta bar ground truth measurement. It's easy to show that strong duality holds, and you can solve the semi-definite relaxation to get your actual solution to the primal problem. So the question is, since in the real world we have noisy measurements, what perturbation in terms of some noisy sensor measurements to this ground truth or noise-free parameter can be tolerated to maintain this zero duality gap? So essentially, how stable is the problem of hand-eye calibration to noise, and can we in fact just solve the semi-definite relaxation? And this theory was developed recently by Cifuentes and others. And if you think of the parameters as living in this high-dimensional vector space, they show that you can, in many cases, prove that there's some ball around noise-free cases. And if your noise lies within this epsilon ball, you can in fact extract your ground truth, your globally optimal solution. So there's more details in my papers, but basically we solve for both the known and unknown scale case. You've got some platform experiencing ego motion that the sensors can measure, and you can use Cifuentes and others' theory combined with proof of a strictly convex cost function and conditions on that to prove that for the known scale and the unknown scale case, we do in fact have this property. And you can, for given values of measurements, you can estimate this, you can calculate bounds on this epsilon. So we've essentially shown that it's a nice stable problem, and in the presence of noise, we'll still be able to solve our convex relaxation and get a certifiably globally optimal solution to our original non-convex primal problem. So to test this out, we started with some simulated data. So we have some sensor platform where there's a rigid link between these two frames, and as it moves around, each sensor measures its rotation and translation, and one of them is scaled, has unknown scale as like a monocular camera. And experimental results basically match the prediction of the theory. So if you increase translation noise from 0 in the measurements to a percentage of the sort of absolute translation between time steps, and here we show that adding extra constraints to our formulation improves our estimation quality. But basically what this graph is showing that for 1% noise, you always get an optimal solution. And even as you add more translation noise over 1,000 runs in each case, you maintain this 100% global optimality result. So this basically means that for every simulated case, we were able to get the global optimum, even in the presence of noise, which matches the prediction of the theory. And each bar in the set just represents a different subset of constraints being used, and it affects the robustness to noise of this resulting solution. So essentially, we've verified with simulated data the prediction of this theory. As for results with real data, we looked at some popular data sets that involve RGBD cameras, stereo camera, an IMU, some Vicon markers for really accurate estimation. And in addition to being competitive with a local solver that incorporates more probabilistic information, our runtime is consistently lower and scales well with the number of measurements. And even in an extremely noisy data set where you're not getting a very good estimate at all, it's able to outperform a competitor method and run faster as well. Other authors have also used our open source software on data sets like Kitty and UROC, and we've consistently been competitive in terms of runtime and accuracy with these other approaches, while also coming with this global optimality guarantee. Okay, so next steps for this line of research include multi-sensor extrinsic calibration. And recent work has shown that you can formulate a similar, not quite handeye, but simultaneous handeye and robot world calibration for multi-sensor systems that include multiple cameras, say mounted on a vehicle, or in our case, we're going to do experiments on a mobile manipulator like this, so you can attach multiple sensors. And they've shown that by jointly estimating all of the relative transformations, you get better results. The problem is that with more sensors, there's more parameters to initialize, and you can have more local minima. It's harder to get a good solution without a good initialization. But we're currently applying our approaches to a formulation that actually exploits the sparsity of the system. So you can scale up to a lot of sensors while having a fast computation time, because you jointly estimate this robot to world transformation Y, and then you have separate transformations for each sensor, and they have this nice sparsity, sort of spoken, like wheel-shaped sparsity pattern where they only interact through one variable. So I'm excited to be working on that currently, and solving harder problems than just a simple hand-eye case. Okay, so we're going to pivot a bit to talk now about inverse kinematics. And this is important for any robot motion, as we saw earlier. And we'll first define what inverse kinematics is. So typically you have an angular configuration space for a robot. For articulated robots, there could be prismatic joints as well, but we'll be talking about angular joints like this. So you have some configuration space, and you have a target or goal position or pose W in your task space. And the forward kinematics function is typically easy to derive, and it's some trigonometric function of these angles, and it's really easy to compute. The problem of inverse kinematics is basically inverting this relationship. You have some goal, and you want to determine the angles that allow you to reach that goal, and it's much harder. And we're not limited to simple robots like this. We're also considering humanoids or hand models, much more complex. Even quadruped robots can have this applied, can benefit from inverse kinematic solutions. Anytime you have some kinematic model, you need to be able to solve this efficiently to reach some goal pose. So solution methods vary from closed form solutions for simple models are really easy to do. For many cases, algebraic methods can be used that can give you full solution sets. There's some famous results on 6 degree of freedom manipulators, for example, that there can be up to 16 solutions for a target pose, but they're limited, and they scale up as you add more degrees of freedom, they become harder and harder to solve and less applicable. So optimization-based or numerical methods are kind of going to be the focus of this talk, and you essentially try to minimize some error between your forward kinematics and the goal while varying your angle. And then there's a sort of whole branch of heuristic methods that don't really fall nicely into any of these categories. So Fabric is a useful example that has this iterative update rule that doesn't really work as an optimization-based formulation. So we'll talk about optimization-based approaches today, because that's the approach I'm going to present, and they're quite popular and flexible. It can be applied to many different scenarios. Okay, so some of you might be asking, inverse kinematics is a very simple problem. What really remains unsolved? You sort of learn how to solve for many robots in basic courses or textbooks. So what remains to be done? So one thing to note is that a lot of the state-of-the-art approaches work really well on chains. So full tree-like and parallel mechanisms are much more complex, like these humanoids and hand robots shown here. And another problem is that workspace constraints pose a significant challenge for safe real-time operation. So when you have a redundant robot that has more degrees of freedom than its task space, so long hyper-redundant chains or something like a humanoid or quadruped robot here, you don't just have a closed form solution where you can exhaustively enumerate over some finite number of inverse kinematic solutions. You need to resort to optimization-based approaches, and it's quite hard to do things like obstacle avoidance or planar constraints on, say, the footsteps of this robot here. And it's really hard to get fast, good performance on challenging problems like this. And finally, formal guarantees are sort of hard to come by. Whether an algorithm will converge, what solution quality is guaranteed, will it be a globally optimal solution if there's some metric for obstacle avoidance, and what the runtime complexity is. These are sort of challenging questions you can ask about many methods, and that make the field still an interesting one. Okay, so to address some of these challenges, we're looking to prior work on modeling kinematics with distances between points on a robot, which are invariant or bounded under joint actuation. So as we can see here, if you fix control points along the axis of rotation of joints, these do not change as the robot moves. So they're constrained in a useful way. So this has been used in conjunction with algebraic solution methods on low dimensional spatial mechanisms like the ones shown here. Whereas our work on IK so far formulates this description as optimization based approaches, including Riemannian optimization and semi-definite programming, and it allows us to efficiently and accurately solve problems with many degrees of freedom, so much more complex mechanisms than the ones listed here. So just to get an idea of what we mean by a distance geometric approach, you can imagine a very simple two-link manipulator like this, a planar case for now. So the approach sort of hinges on elements of what's called the Euclidean distance matrix, or EDM. So given a set of n index points, the entry in column I and row j encodes the distance between the ith and jth points. So for a simple two-joint planar manipulator with points fixed to its joints and end effector, we can describe the manipulator's feasible configurations with constraints on the corresponding EDM entry. So for example, the fixed joint lengths correspond to exactly known elements in the EDM. And similarly, symmetric joint angle constraints become bound intervals on distances between points adjacent to the joint being actuated. So that's P1 and P3 here. And we'll also see that it's useful to square these constraints in our EDM to get a purely quadratic formulation like the one we had with the sensor calibration earlier on. So you just square the distances and you get quadratic equality and inequality constraints. Okay, so just to show a few more examples of this in cases other than the planar case here. So you've got spherical joints and then this more generic revolute manipulator. You basically have this simple procedure for transforming a broad class of inverse kinematics problems into partially known Euclidean distance matrices for a variety of manipulator types. So you've got fixed lengths defining these equality constraints. You've got inequalities defining angular limits. And you define your goal poses by distances to the base points of a manipulator. And when you square all of these constraints, you get a quadratic feasibility program. So you're trying to find a position for all your joints such that these equality and inequality constraints are satisfied. And we're once again back to quadratic programming like we were for sensor calibration. So to sort of go in a bit of detail on what it looks like to take a semi-definite relaxation of this resulting quadratic feasibility program. Once again, with a two-link manipulator, we've got a target right here, and we've got a circular obstacle that's embedded in the ground right here. And we start with this quadratic feasibility program where x is the position of this joint, and you've got constraints on the link lengths here. So from the origin to this position has to be a unit length, and the distance to the goal has to be a unit length. And we've got obstacle avoidance constraints in the form of inequalities here. So we'll once again be interested in taking a semi-definite programming relaxation. So we define this rank 1 Z matrix again. We include an S variable to homogenize any linear terms. So it's a purely quadratic program. And this is what it ends up looking like. And you end up with a relaxed semi-definite feasibility program. So instead of finding X in this quadratic constraint subject to quadratic constraints, we get a semi-definite matrix Z subject to these linear constraints. And it ends up looking like this. If you reduce a lot of the variables down, you can plot it in 3 dimensions. So the feasible region is this pierogi or taco shaped structure. And the 2 possible solutions, the elbow up and elbow down, are at these extreme points of this spectrahedron, as it's called. And the obstacle constraint enforced by this object here is this half plane constraint. So that gives us that this is the only actual valid solution. This one represents an obstacle collision. Okay, so we've taken a quadratic program and turned it into this semi-definite one once again. And the question is, for a low dimensional toy problem like this, you can observe where the solutions are and easily interpret it. But for more challenging higher dimensional problems, actually interesting problems, how do we search this convex body, the spectrahedron, for these solutions? And the simplest way would be to, instead of just doing a feasibility program, we want to define some sort of optimization. So you include some linear cost in your variable, and we have to choose it in a way we hope that will allow us to find an actual solution. And because it's a linear cost, just like in a linear program, how choosing a direction sort of points you towards the boundary of your feasible set, the same thing is true here. So we basically want to choose a direction. The cost matrix can be thought of as a direction that points us at our solution. So this takes our problem from a feasibility one to an optimization, and the solution is on this boundary somewhere. So how do we choose C effectively? In the simplified planar and spherical cases, in our ICRA 2020 paper, we showed that we can actually do something similar, inspired by the global calibration stuff I just showed you. So you can actually define your feasible set as this algebraic variety, which is quadratic once again, and then you can do a nearest point formulation. So just like we showed that you can perturb a noise-free calibration instance and still have global optimality, if you have a solution, but you guess a point that is not close, that's somewhat close to that solution, you can show that you're guaranteed to get a solution. So essentially, you can guess a set of points that that are not actually a feasible solution, but if they're close enough to an actual feasible solution in terms of Euclidean distance, then you will actually have a tight SDP relaxation and be able to solve this problem. So it was inspired by that machinery for stable noisy estimation. There's no noise in this case. The noise is sort of just the fact that you don't have an answer up front, but if you guess a random solution, you can, and we empirically show as well, you get a solution most of the time. You get a globally optimal solution. So it's really cool to see that work for planar and spherical cases, but for arbitrary revolute 3D manipulators, when you're not in a plane or you don't have just spherical sort of shoulder joints for all your joints, it does not apply. So the conditions required do not work. And it's actually sort of related to rigidity theory, which studies whether a truss of points will be rigid. And so there's some interesting reasons why it doesn't work, but for now, we'll just move on and say, okay, we need some other solution. You can't just randomly guess a configuration and then try to do a nearest point based optimization. Okay, so since distance geometry problems show up in a ton of other fields, including sensor network localization, indoor localization, acoustic problems, and biomedical imaging problems like molecular conformation estimation, we decided to look at the literature and also just see which problems are most similar to our inverse kinematics case. And we found that wireless sensor networks and molecular conformation had the most relevant literature to get a sort of similarly defined problem. So we took a look at solutions to these problems. And most importantly, we looked at sensor network localization. That literature had the most relevant work and found there were actually a few methods we could try. So one thing to note is that all these other problems are noisy. In our case, we're assuming we have an exactly known robot model. So there's not really any noise in our constraints. We have to actually obey our kinematics constraints exactly. They're not noisy measurements. In all these other cases, your constraints come from measurements between objects that are potentially corrupted by noise. So with that in mind, we dug into the literature on sensor network localization, and there's actually work in the base noise-free case if you have extremely accurate sensors or just theoretically analyzing the problem. And there is a ton of research into using SDP relaxations to solve this problem. But the theoretical result of interest is that you're only guaranteed a tight SDP relaxation. So this is our, in different notation, our QCQP describing inverse kinematics. So it's only going to be tight, the SDP relaxation of it, when there's a unique solution to your problem. But we've mentioned that we're interested in solving inverse kinematics for redundant manipulators when you have potentially infinitely many solutions. So there is no unique solution. So we don't have a guarantee that our SDP relaxation will be tight, which is interesting. It's a bit counterintuitive because this trouble comes from the fact that there's actually many solutions, but that actually makes it harder in the case of solving it with this method. Okay, so with that in mind, we looked at some methods used for SNL, and we found this convex iteration approach, and we came up with Sigic, which is convex iteration for distance geometric IK. So we start with our SDP relaxation over here, and we use the identity matrix as our initial cost function, which you may know is the nuclear norm heuristic that's used in a lot of other fields, but it's just an easy starting point. And then the idea here is to iterate between solving this and then solving a problem that seeks to find a new cost function for an SDP that basically approximates the excess rank or eigenvalues greater than the dimension that we want of our matrix. So this procedure chooses a cost function that lowers the rank of our estimate. And as we saw in our pierogi a few slides ago, the low rank solutions that we want lie on the boundary. So we iterate between suppressing the rank and then minimizing our constraint violation back and forth. And this is from De Toro. It's got a nice textbook on distance geometry, and it's been applied successfully to sensor network localization. And this worked really well and was quite fast for our problem. So moving into some experiments we tried with it. For a very simple start, we took some robot arms and we put these sort of large platonic solids like an octahedron and a cube and an icosahedron around them. And we compared with a traditional sort of local optimization with angles-based solver using SLSQP, sequential least squares programming. And what you see here is the position error, the logarithm of the position error on the x-axis, and the rotation error of our posed goals on the y-axis. And the shaded in region is sort of an acceptable tolerance of 1 centimeter and about 1 degree or so of error. And over many simulated goals, you can see that our Sigic method lies within this acceptable tolerance region more often than the local angular solver using SLSQP. And this was just a simple toy problem to start. We used 3 popular industrial manipulators, and they're sort of unrealistic object placements, but they were a simple way to start. But it's a good start. Other than in the UR10, it's still a little better than the SLSQP, but it was challenging. But for the KUKA and the Shunk robot, it was much better performance. So bringing it towards a more realistic problem environment, using 100 spherical obstacles, and this hyper redundant manipulator, so each of these joints is either 2 or 3 degrees of freedom, we achieved a higher success rate than the SLSQP algorithm while being about an order of magnitude faster and just having lower average position and rotation error overall. So this is much more realistic, and it's interesting to note the solution time as you increase the number of obstacles didn't really scale up. And we saw with the pierogi that each obstacle is sort of like adding a half plane constraint to our feasible set. So it reduces the volume of the search space. So in some ways it might reduce the complexity of that search, even though it is another constraint to enforce. And yeah, we're curious to keep trying more and more complex environments and robots and seeing if this performance gap persists or even grows. So remaining work to be done in this area includes the fact that currently we're limited to robots whose successive axes are coplanar. And this is a big limitation right now. If you don't have this property, there's a chirality issue. You can get mirror reflections of your actual physical geometry that are not physically realizable. But this can be resolved by including auxiliary variables and enforcing sort of cross product constraints between the relative positions of these points. So that's something we're working on. And like I mentioned, increasing the number of obstacles and the complexity of robots being used is an important next step. And one interesting point to mention is that since each control point on our robot is only constrained by neighboring joints, we have this nice chordal sparsity property we can show holds for the structure of our robots. And using a chordal representation of your variables, you can actually have a much more efficient solver than just a vanilla SDP solver. So that's a direction we're also investigating. One really exciting area for future work is this notion of distance geometric motion planning. So instead of just inverse kinematics, if you have a full motion planning problem description with obstacles and some manipulator in an initial configuration, you can define across time steps a configuration, a variable configuration for the robot until it reaches some goal pose. And you can essentially try the same approach on this QCQP. So you're just limiting each node through time's motion. So there's a different variable for each position at each time step. And the cool thing about this is that that sparse property still holds. So even though it's a ton of variables and is a very high dimensional, difficult to solve problem, you can use this chordal sparsity property to potentially speed things up. So that's something we're working on. That's going to be potentially interesting, but still a lot of work to be done. And yes, hopefully the sparsity will aid in making it feasible to solve. And the reason this is interesting is that local optimization and sampling-based planners are kind of the two main paradigms people use, and the local optimization is typically in the angular configuration space. My hope is that because motion planning is hard and these different types of planners excel in different scenarios, maybe there's a niche that this fits into. There's not going to be a silver bullet because it's just computationally hard. There's not going to be some single best method. There's no free lunch. So we'll see how it works. So let's see how I'm doing on time. So final topic is going to be deep representations of robot geometry. So in around 2017, Amos and Coulter did this OpNet approach where you can embed quadratic programs into neural networks, and they showed how to differentiate through the solution to do back propagation required for training neural networks. So inspired by this approach and recognizing the sort of quadratic cost and constraints here, my colleagues and I thought, well, can we use QCQPs over rotations? We know we have quadratic constraints for rotation elements. It's not quite the same formulation they did, but this line of thinking inspired this idea of learning a cost function over rotations rather than directly regressing to rotations for deep learning applications. So an example would be if you wanted to do a deep approach to hand-eye calibration, instead of just having your network directly regress the rotation parameter, you could instead say, okay, we're going to try to learn the cost function. It's a bit more interpretable. It'll perhaps work better. And then we can, as a layer in our neural network, solve that problem parameterized by the cost function and see how it works. So we used the unit quaternion representation of rotations for this approach, and found that it's with this nice little approach, it's actually can be solved in closed form as an eigenvalue problem, much easier than treating it as a generic QCQP. And it actually led to this nice little solution that is equivalent to Bingham distribution. So you can parameterize a Bingham distribution over unit quaternions with this matrix. And it's very simple to use in PyTorch, and we found it worked quite well. We also found that it has nice continuity properties that allow back propagation to produce nice derivatives in a way that other representations don't. So regressing directly to unit quaternions causes problems in this area. There's a discontinuity that it's hard to train over. And yeah, we essentially show that our approach has this nice smooth mapping that lets you learn over it quite well. So in terms of performance, point cloud alignment was one of the main tasks we tried it on, and we compared with just regressing quaternions and another approach that has this nice continuity property, and found we had really good results over some synthetic experiments. And the regressing to quaternions in particular suffered when you have rotations that are close to 180 degrees, so larger magnitude rotations in your data set. We also found that it had this nice out of distribution detection property. So we had a data set with a aerial vehicle with a global shutter camera that had to transition between an outdoor and an indoor environment. So if you trained your localizer based purely on outdoor data, the 4 representations here perform pretty similarly. But when you have a data set when you train in one data set and then have at test time examples from another out of distribution data set, our approach had a natural ability to sort of have a robustness to this change in environment. And then a final point about learning, some of my colleagues are currently working on a very general purpose generative model, which can do inverse kinematics for a variety of robots and problems. And it's using graph neural networks that use this distance geometric approach. And the hope is that because if you can describe your problem purely in terms of distances between points, you're not tied up to a particular robot's configuration space and kinematics. You can have this sort of distance geometry engine internally that lets you solve many problems. And yeah, that's active work they're working on right now, which I think is an interesting direction. So I want to thank my frequent collaborators, and I hope to see some of you at ICRA in Philadelphia. We'll be presenting on Sigic, the inverse kinematics approach. You can also check out some of the software I've written with my colleagues on all of these topics. So thank you everyone for listening. Happy to take any questions.
Okay, thanks, Matthew. Yeah, let's open the stage for a question from the audience.
So I have a question. The part where you spoke about learning cost functions, can you speak a little bit about relationship with like energy-based models where you, or as they should be called, maybe implicit models, where you also just learn a cost function and then obtaining whatever you need is just done by optimization?
Yeah, so there was, I think there's a paper that does it specifically for rotations, wasn't there recently? So I haven't looked at it in a while. I'm not sure. Yeah, I'm not sure. I know that that paper had really good performance on a lot of problems. But yeah, I don't know. I don't quite remember exactly what they did, or what they're like. Yeah, I'm not sure if it uses something. Is it like a specifically a quadratic energy they define or something? I'm not. Yeah, I'm not too familiar.
I have not seen this in the context of geometry. It's more that in general, like if you do learning with energy-based models, you basically don't, particularly if you have like neural networks, you don't train the networks to predict what you actually want to know, but you train like a cost function or an energy function. And then you get a result by optimizing that energy function.
Gotcha. So yeah, I should look a bit more into that. I gotta, sorry, 1 second. Yeah. But yeah, I think that philosophy is similar. Yeah, to me, it just makes sense to not regress directly to some parameterization of of some space you're interested in.
We have more questions for Matthew. Okay, if you have a question, just unmute yourself and go ahead.
Can I ask a question?
Yeah, Hannah, go ahead.
Hey, Matthew. Yeah, no, I guess I had like a more general question about like how you connected these topics and how you came across like this line of research. I guess like how did you go from, you know, hand-eye calibration and then, oh, you had this idea, or like what's the story behind following this line of work, if you don't mind me asking?
Thanks, Anna. That's a good question. I think the main weird jump was in this nearest point formulation of inverse kinematics. So yeah, I guess my colleague and I were just looking. He was looking into Philippe was looking into manipulability aware inverse kinematics, and we were just having a conversation about quadratically constrained optimization problems. So yeah, just like thinking about a sort of like planning type problem like IK, where you want some goal as like this dual to an estimation problem, where you have this, you make a random guess and you try and get as close as possible. That was kind of what caused the pivot. But also I think it's just a bit of maybe a syndrome where if all you have is a hammer, like everything starts to look like nails. So I was just reading a lot of convex optimization stuff and STP relaxation based approaches to things. So that might explain a lot of it. But yeah, I think, yeah, just with what I was reading at the time.
Really cool. I have like more questions, but if someone wants to go before me, speak now or forever hold your peace. I guess, can you go to the motion planning slide again? I wanted to ask like clarify some of my understanding on that. This is okay.
Definitely. 1 second. Yeah. Yeah, it was a bit rushed. This one, right?
Yeah, I guess like what I wanted to ask is just, can you go through this again? Like, I'm not quite sure how you're using the distance geometric representation to get like motion planning, and what are the no free lunch of this idea? Like, what are you trading off here?
Yeah, so yeah, so this is still ongoing work, so I don't have any results to speak of yet. But basically, what we're saying is that instead of just defining a distance geometric constraint for a single pose, you're taking n poses, and you're defining the first one to be equal to your initial configuration, and the last one to be your goal pose. And then for every time step, you have a whole set of variables describing the position, the configuration of your robot. So it has the inequality constraints that prevent obstacle collision, and it has the geometry constraints like the fixed joint lengths. And then what we're saying is that to ensure that they're sort of connected, that you can actually move between them, you limit the displacement of each individual node's movement between successive time steps. So that's in the form of quadratic inequality constraints. And you solve that whole thing as a single batch QCQP, and you relax it to a semi-definite program. And so basically, yeah, the hope here is that, so like with sampling based planners, for example, they have really nice like completeness guarantees, and you can do things to speed them up. But they'll sort of maybe suffer from like bug trap scenarios or something, where there's a thin, in terms of volume in your configuration space, there's like a thin passage or something. And so local optimization methods that use angles can often do much better if they're given an initial configuration that's close enough to that. They can optimize through something like that. But it does depend on having a nice initial trajectory to not get stuck in local minima. So my hope is that there will be some subset of problems for which this approach is good or can seed local optimizers in an interesting way. And it's still, yeah, I'm still working on implementing it, but I'm excited to see if it works well.
Cool. Okay, so it's not like a recursive every time step thing. You're treating the whole like series of motion as like a batch problem, including like maintaining constraints for every configuration and between configuration time steps.
Yes, and because you only need to do, between time steps, distance constraints, you have chordal sparsity in both the space and the sort of time dimension. So you can use like a Cosmo is a sparse SDP solver that's quite fast on problems like that. Because otherwise it would just be way too large of an SDP. Well, there's other ways to address it, but you typically need to exploit some kind of sparsity, which this formulation does have.
Okay, pretty cool, pretty cool. I have another question. If there are other questions, please go first. I guess I'll ask it. Can you go back to the slide? Okay, I don't have the slide number, but the slide where you show the relax problem and the dual problem again.
Oh, yeah. Yeah.
I think it's like really early on. Yeah. Yeah, I just wanted to go over this again. So you're saying that, okay, I guess like from what I looked at, you're looking at the dual primal gap. So I just wanted to know like, yeah, maybe I missed this, but what's the role of the relaxed problem versus the dual problem? Like if you can show that there's no duality gap between primal and dual, then solving the primal is the dual. So then, yeah, I guess this is where I'm confused. Like what's the role of the relaxed problem?
So just depending on the particular problem and the number of constraints and just the structure of a specific problem, this can be faster to solve. So like a lot of theoretical results just deal with determining this gap. So if you know that this gap is 0, that if P equals D, then you also know that P equals R. So in terms of tackling the theory, you just typically look at this arrow. And then you get this one kind of for free. But yeah, to answer your question, it's often just faster to solve. This is often called the primal SDP as opposed to the dual SDP. But yeah, it's kind of on a per problem basis, but I've found that at least in calibration, this is usually quicker to solve.
Compared to the dual SDP, right?
Yeah.
Oh, okay. Okay, I thought you were using both and then I got confused, but yeah, okay, that makes more sense.
Gotcha.
All right, thank you. I think that's like all my questions for now.
No problem. Thanks, Anna.
Thanks, Matthew.
I have a follow-up question. Do you always assume that the points or poses are reachable? And what happens if you have unreachable poses or points?
That's a good question. So for the inverse kinematics, right? Yeah, like
yeah.
For unreachable poses, so that's like other works have tried to use like branch and bound solvers to provide certificates of infeasibility, and they're like slow, but they work well for saying like, yeah, we know this problem is not solvable. This I was at first hopeful that we might have that property with this approach, but because the SDP is sort of like, it's like relaxing to higher dimensional manipulators, so you can have them in like 4-dimensional or at higher space. What it'll often do is just kind of give a solution that like goes through around an obstacle or something in a higher dimension. So it usually does not let you reject unreachable poses. Like sometimes it does, like in cases that are really cluttered, but in general, it's not a method for certifying the infeasibility of a pose, the unreachability of a pose. You'll just find that the Sigic iteration will converge at just some semi-definite matrix Z that's high dimensional. And we don't have any theory worked out that says that guarantees a solution or conditions under which you know that there's no feasible solution. So it's not, to answer your question briefly, no, it doesn't reject infeasible poses, but it tries to solve them, and it'll give you some high dimensional, some higher rank Z that corresponds to a bad solution. You can project that solution down to a lower dimension, and you'll just see that it'll hit an obstacle or something. So yeah, but it's no theoretical guarantee or anything.
Okay, thanks.
No problem.
I think we don't have more questions. Yeah, again, Matthew, thanks for your time. And this was a really interesting talk.